I communicate my science to the people that ultimately is supposed to be unemotional, but I often get emotional responses back. And it is very, very fascinating to me to see how my unemotional science is emotional to people. It's quite exciting in a way.
Hello and welcome to SciLux, the podcast that is for people who love science and for those ones who don't yet know that they do. And today we're crossing the borders a little bit further than usual. So as you know, we're talking to European scientists, and we're talking to a scientist that used to be in Luxembourg, but right now is in the US. And our guest is Sophie Nuber, who is a climate and marine scientist at the University of Washington, Department of Oceanography. Sophie is originally from Luxembourg, as I said, but when we're recording it, it's 2 days to go to Young Women's Conference Luxembourg, where she will be a keynote speaker. So we cannot say how the keynote went, but we can say what it will be about at a certain moment as well. Sophie, thank you so much for coming today.
Thank you so much for having me. It's great to be here.
Climate change again, in a way. It's difficult to be positive or not. How do you take it? What's your take? When you wake up in the morning, you say like, today I'm going to change the world, or just small steps?
I want to say that when I was young, that was my aspiration. I was like, I'm going to become a climate change scientist because that's where I can do something good in the world. But also really because it was a part that I was frustrated with. It's really exciting to be here because when I was preparing my presentation for the Young Women's Conference, I asked myself, like, why did I end up where I am? And mostly it's because when I was their age, it was 2008, for example, or 2007. And you can imagine what kind of world that was. In 2007, they came out with the iPhone. In 2007 was I don't know if any of you remember, there was a huge sort of Earth for the People concert where, they tried to collect money for climate change and raise awareness. But also Al Gore's movie that's really, really famous only came out in 2006. So I grew up in a world where media would put a climate scientist on one side and I don't know, whatever you would like, economist or whoever else on the other side, and it said, go discuss. So out of that came, only climate skepticism. And of course, that kind of process is not useful because you should have climate scientists discuss with climate scientists, right? That is discussing apples with apples. And if you had a look at the stats, you would see that 99% of all climate scientists at the time thought that climate change was real. But that didn't arrive at my education. I was a 17-year-old thinking about my career. And so I was just sitting there going, why do these older people up there not figure this out? I mean, climate change is a natural phenomenon. How is it that we cannot explain this? This should be explainable with, physics, chemistry, biology. I mean, this is not a political idea. This is something that goes on in our world. And how is it that these, old people can't figure this out? And so, as a young, kind of full of myself little girl, I was like, well, if they can't figure it out, I'll figure it out, And so my decision to become a climate change scientist was very much based on this misunderstanding that was projected by the media and this drive to do something useful, maybe not good, but useful in the world and provide knowledge that will really put us forward, that solves a problem. And so because that has always been my standpoint, I've kind of seen the whole, in my professional life, I've kind of seen the whole thing very pragmatic, I have to say. So to me, it's always very, very interesting to disentangle the emotion that people have with climate change from the science of climate change. And I get in touch with that a lot through my art and science projects where, I communicate my science to the people that ultimately is supposed to be unemotional, but I often get emotional responses back. And it is very, very fascinating to me to see how my unemotional science is emotional to people. It's quite exciting in a way.
And from your scientific eye viewpoint, are these the right emotions?
This is an interesting question. I would say they are predominantly scared. So I would say predominantly the people I get in touch with that have emotions towards climate change, they are scared, they're worried, they are confused. Sometimes just yesterday at breakfast in this hotel, I had conversations with two others, one of them being a computer scientist. He was here to visit LIST, Luxembourg Institute of Science and Technology. And he's a scientist himself. And he didn't know really what the data for climate change shows. And then there was another person who was here for a music event. He also had no idea what actually the data for climate change is. So they effectively base their opinions on what they hear in the media, and they need to trust that there's trust in their belief. So they either trust the media to say the right thing, or they don't, and then they become a climate denier. So in that sense, it's very, very interesting because there's a lot of confusion, a lot of fear, a lot of anxiety over this trust that these people have to put into the media, because we know today media is not always trustworthy, right? So I really feel with them. And what I'm trying to do is to break that fear, that anxiety, purely by giving facts and putting things into perspective. So for example, I work with an artist called La Benita Hui. She's a very well-known artist in Taiwan, and she makes huge panels out of plastic pieces that she collects from the environment. But in one of her pieces, we decided to show the sea level rise visually of 5 cities around the world. And the idea here was that people come with anxiety over the idea of sea level rise. But what we don't know is what is actually sea level rise in our city. We don't know what is it in other cities. Are we well off? Are we not well off? Do we actually have to worry about ourselves, or do we not? So the idea here was that if you walk along those panels of these different cities, you can visually feel how high is sea level going to be. For example, in Taipei, which is the capital of Taiwan, the prediction for sea level rise for 2100, given the highest CO2 release that we could possibly have, would be 90 centimeters. And so we made a visual change of color at 90 centimeters. So if you stand in front of that panel, you can feel on your own body where that 90 centimeters would be. So you can feel and you can know what does it mean to have 90 centimeters. By giving data out, we are trying to calm people's minds. And if our data is creating more anxiety, now, hopefully, this anxiety is at least based on facts and can be directional. Now someone can make an informed decision and say, I am scared about this. Maybe this is worrisome to me. But what I want to work against is the anxiety based on I must trust the media, or I must trust information that comes my way, which I actually didn't understand completely, or I don't know where it comes from, or I don't know why they say that. And if I listen to another channel, I hear something completely different. That's my goal. Yeah.
My feeling is that when you ask scientists about data, the first answer you get, it depends, right? So it's very difficult to then do science communication on it. And we are not exactly sure on all the exact data there, right? So how do you choose? Aren't you scared that in the end you're not 100% sure about the data you're communicating?
The error bar on data is a very, very important point in science. And obviously, as scientists, that is all we talk about. So someone that hasn't really done science communication before is going to nail down on those error bars because that is all we care about as scientists. But what as scientists we sometimes forget is how much we do know. And the fact is that error bars, again, are effectively an unemotional expression of how exact we know something. But they also show what we know because the error bar has a stop. And anything outside that stop is virtually unlikely to be the case, right? So for example, I do a lot of PCO2 reconstruction. That means I'm looking at greenhouse gases in the atmosphere and I'm trying to see what the variability of these greenhouse gases was like in the past prior to when we started to measure them. So we know today that effectively almost every climate change that the Earth has had, let's put a bracket around some of this. Here we are, arrow bar. Some of them are different, but a lot of them have to do with the greenhouse effect. So the idea that when you have more of your greenhouse gases in the atmosphere, it's kind of like a blanket for the Earth. So if it is winter, I'm going to have a thicker blanket, maybe full of down. And in the summer, I'll have a thin one, maybe just a sheet, right? And I'll be cooler under the sheet than I'll be under the thick winter blanket, that's not because I produce more heat in the winter. That's because the blanket is better at reflecting my own heat at myself. So I'm keeping the heat in. And the greenhouse effect is exactly the same thing. The more of these gases we have, the more we can keep the heat in. So the energy we get from the space is still exactly the same, but we're sort of keeping it in Earth rather than giving it back to space. And that effectively drives almost every climate change, including our own. And so if we really want to characterize whether our current climate change is, for example, whatever that means, normal or abnormal, or is it fast? Is it slow? We can go back in time and we can see, well, has this happened before? How often has it happened? How fast has it happened? And so we started on Earth to be measuring this CO2 in the atmosphere as a representative of all greenhouse gases in around 1960s. Now, if you look at the curve and the data since 1960s, it's basically a straight line. And it starts at a number. This number is, whoever's listening now, don't worry about this number, but this number is like around 310. But like, what does that mean? Like, does it mean that 310 is normal? Or is it that we should have started measuring at, 1950 and we would have had a starting point of 290? Or what does it mean? And ultimately, I'm going to tell you, it means nothing. Like, we do not know, just looking at this line since 1960, we do not know what the normal is. And so my job is to go back in time and make sure that we know. And so, for example, we're just publishing a new record which goes back 1.5 million years. And so we're really looking at how does CO2 as a representative of greenhouse gases, how do greenhouse gases change over this long period of time? And what does ours look like today? And if we look at that, we can see that today is 1.5 times higher than the maximum of the last 1.5 million years. We can also see that how fast it changed. We have the rate from 1960 to 2026. We have crossed so many numbers. So today we have around 423. So from going from 310 to 423 is more than 100. And the unit, for anybody who's interested, is ppm, by the way, but we don't need to go into that. But it is more than 100 ppm. And in the last 1.5 million years before sort of humans were releasing fossil fuels, we had a change of 100 ppm, but they always took 10,000 years. So, of course, we have error bars on these measurements, but our error bars are something like 20 to 40 ppm, not 100 ppm. So, yes, we have error bars, but it is really, really important to understand where the error bar ends.
In this podcast, we often discuss data collection because it's so important for scientists, right? So you just made me think, I always assumed that if you don't collect the data, you don't have it. So how can you have the data of the CO2, 1,000 years ago? That's impossible. Or where do you get it from?
It's so cool. It's going to blow your mind. We sometimes are very human-centric. We think that we are the only species on Earth that knows about stuff. We're the only species that can collect, that can measure, that can do science. If you look under a microscope and you look at something tiny, 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 you will be surprised sometimes how beautiful these things are. And if you think, I wonder why they're beautiful, you start looking at them and it turns out that, the way they put their chambers together is like in the Fibonacci row, or it's in, maybe you've heard of the golden rule, things are in the golden. All of these are mathematical rules. And so that's fascinating. But have you considered that the Earth is collecting its own data? Have you considered that the Earth might be smarter than we think? And this is exactly what we're making use of. So we on the planet have something, well, as humans, we call it natural archives. And it is ways where the Earth, over geological timescales and shorter timescales, longer timescales, has been effectively recording its own history and its own climate in chemical and physiochemical or biogeochemical signals. Effectively, all I have to do is collect the archive and unlock the signal. And I just need to understand how this signal is linked to the environment. So to give you an example of my work, I work a lot with corals because they are one form of such a natural archive. And I also work a lot with what's called foraminifera. They're another type of natural archive. Both of these are calcifying organisms. They both live in the ocean and they calcify. Just in case you think you don't, you calcify too because you've got a skeleton, but your skeleton is on the inside of you. The difference to these ones is it's on the outside. So corals, for example, these are sclerotinian corals, so they make these huge reefs. Coral reefs are effectively carbonate, which is made from calcite and CO2. And they live on the inside of the reef and they come out through tiny little holes. They come out and filter feed or do photosynthesis through their symbionts or something. Forams are similar. They are effectively a bit like snails. So they've got a little house and they live on the inside. And when they die, you can use them. You can dissolve them in acid, for example, and you will now have a liquid that has all the little elements inside that went into this shell additionally to its calcium carbonate. And the way that these elements were put in there by the organism is directly linked to the environment that they lived in. So if we want to, for example, find out what the CO2 is like, we can use foraminifera because when they grow, they build in sort of accidentally, they put in the element boron into their shell. And boron, or the isotopic composition of boron, has a direct link to the pH of the seawater that they lived in. But because they live in the open ocean, the pH of the seawater is very sort of like kind of global. I mean, there's local variability, but reasonably global. And so what we can do is calculate directly back from the pH in the seawater to how much CO2 was in the seawater, and that is directly linked to how much CO2 was in the atmosphere. So we can use the chemistry of these shells to back calculate variables that matter for our climate.
But effectively, we're looking at species that live now. So do they pass it on?
This is a good point. Foraminifera live right now, but they've been living for millions and millions of years, and they've been living all over the ocean. So when they live around 2 to maximum 4 weeks, and when they die, their shell, which is calcium carbonate, cannot really be eaten by anybody. So they just fall through the ocean on the ocean floor. And then you've got other stuff falling on the ocean floor. Ultimately, you've got your ocean floor layering with time. And when we come in today, we can take a drill core from the ocean floor, and they can be very long. They can be up to 300, 400 meters. We can take them from up to 6,000 meters depth. So these are huge ships going out with huge drilling platforms, almost comparable to oil drilling projects. And the work that I do is usually a little bit shallower. We get cores from 2,000 meters. The benefit is that the shallower cores have less dissolution effects, less what we call diagenetic effects. So basically, these effectively fossils that we pull out of these different sediment layers, they are less changed. So they are much more exact like what they were when they first fell on the ocean floor and got buried. In the depth of the ocean, the chemistry can vary. And so the quality of the fossils that we find there is not always as good. So we usually go to about 2,000 meters depth, drill there, take about 300 to 400 meters worth of sediment, and then we can go back in time. And depending on the sedimentation rate, so like how much sediment falls on the ocean floor every year, we can get a different resolution. So the material that I work with, for example, we can get one measurement per 1,000 years. So per 1,000 years, that location acquires about 2 centimeters of sediment. And because it is undisturbed, it's the ocean floor. What's going to happen? You know, there's nothing's going to come from the bottom and mix it up unless you've got a volcano. We make sure that's not the case. Then you can go back in time. 1,000 by 1,000 by 1,000 by 1,000 years. And so over time, you can end up with 1.5 million.
This is really, really impressive. So our listeners are already used to the fact that normally in our podcast, the guest asks the so-called pub quiz question. But as we are meeting around Young Women's Conference, I wanted to flip it a little bit. And today I will ask the question to the listeners. And probably when you'll be listening to this, you will already be able to find the answer. We don't know it yet. The question is how many young women and girls were participating in Young Women's Conference. So go check it out. And if you're not satisfied with the answer because you think I wasn't there, then remember, most probably it will continue. So you can check out Young Women's Conference Luxembourg and register for the next year. But that's just obviously a little bit of shameless advertising because we're meeting because of that. And I'm involved as well in the conference. But going back to what you said, how many samples do you actually need to collect to know the whole Earth picture?
This is a very good question because actually you're touching on a problem that we not really have solved entirely so far. I'm going to call it the problem of scale. And the problem of scale is that depending on what time you're looking at, you will have a different resolution of time. So I was just saying, we looked at the last 1.5 million years. We have a data point every 1,000 years. But then, for example, if I could do the same type of reconstruction using corals, but corals only live for 100 to 200 years, maximum 300 or something. Sometimes you can also use multiple corals and, for example, one that is alive today and then various like fossilized corals, and you can maybe make a longer record. The thing is, with corals, you would never be able to reconstruct 1.5 million years worth of history. But what you can do is, because they grow every year, you can have a data point every year. Whereas with my forearms, if from the ocean floor, I can only have a data point every 1,000 years. But I can go back longer in time. So you can see that there's a, so to say, problem of scale where the resolution is linked to the archive, and it really depends on what question we're asking, what kind of resolution we're getting, and how far back in time we can go. And the crux of the whole thing is now, how do we put them together? If I have a coral that gives me 250 years of data, but my foraminifera sediment core gives me like my first data point is effectively an integration over the first 1,000 years, how does that 250 years fit in there? And that is something that is ongoing research. We need to find innovative ways to bridge these questions of scale. Give an example of Luxembourg. So Luxembourg suffers from a lot of heavy rainfall at the moment, and that can lead to flooding in the country, but it also leads to flooding in its neighboring countries, for example, in Germany or in France. And we have incredible data for the last maybe 60 years of like how this rainfall has happened. But rainfall is also very, very patchy. Maybe you know it can rain in Luxembourg City, but then in Strassen, which is outside, it already doesn't rain anymore. So it's very patchy. How can you reflect that? And now we have to think even bigger, because climate change is not a weather phenomenon, it's a climate phenomenon. So the difference between these two is scale again. Weather is what happens at your own place for a couple of days or a couple of weeks. Climate is what happens in your region for multiple months or years or even decades. And so again, how do we link something that is so small scaled, the weather that we experience, extreme weather, for example, extreme events, how do we link that to climate change? This kind of attribution science is ongoing at the moment, and I'm getting my feet wet in it as we speak. So yeah, I'm trying to put forward innovative solutions to bridge these scales. And one of my solution suggestions is to use these different archives and try to link them together. So in the Luxembourg example, using archives from Luxembourg that can reconstruct the high variability of rainfall in one location, but then using the marine archives, the ocean archives nearby to reconstruct the long term, and then having a look, how do they fit together? What kind of stories can we tell? Because what we can also need to say is that the shallower we go with, for example, ocean sediments, the higher we can push the sedimentation rate. So if we are near a river, we get much more flux and much more stuff coming into the ocean, which means that we get more than just one data point per 1,000 years. And so by making a transact, a local transact, we can effectively cross the border from something that is a deep ocean to a shallow ocean to a river to a terrestrial site. And that is a potential for bridging the spatial, but also the temporal gap.
And if you want to know more about climate and weather and what they mean altogether, you can go back to one of the episodes we recorded a couple of months ago with Andrew Farone, based also here in Luxembourg. He's also involved in the IPCC reports and everything, so you can listen to that. But probably a lay question, but I don't understand one thing. So if you get that data point, let's say you go down somewhere in the ocean, you get the data point, how much does it cover? Because what you're saying is, okay, you're combining those different archives, but then where's the overlap? Or like, is it only the, 10 meters around the place where you took it?
That's a very good question. I've received this question many times, and it is actually also a discussion point between scientists. But here is partially my take on it, which represents the view or the science that we do in my field. The criticism is that if you only take one sediment core, you only have a local signal. That can be true. But ultimately, it depends on the system that your sample came from. Because if it comes from the ocean is an inherently mixed signal. So, for example, when you go to a beach, you know that usually, sometimes depending on the beach, there can be variability, but usually the temperature, if you go into the water on the left side of the beach or the right side of the beach, the temperature feels remotely the same. Maybe your wave action can be different depending on the floor, but ultimately the water will feel the same. So the ocean has quite a large spatial mixing area, and that means that we can assume that our data point is valid for at least the region. Now comes another part. In the ocean, we have ocean currents, and these ocean currents are very predictable. They don't just change on a daily basis. For example, the atmosphere can change on a daily, even hourly basis. You can wake up in the morning and in the afternoon it hails or it snows or something. That is crazy, but the atmosphere has an incredibly fast pace. The ocean doesn't. So the ocean will take months to change. And that means that it's very, very predictable. So even though we have only one data point, we can actually predict very, very well what this data point means. So for example, if we measure, this is a very common example from the Pacific, off the coast of South America, they have something that is called an oxygen minimum zone. So there's an area in the ocean where oxygen is very depleted. And you can follow this signal along the ocean currents through the Pacific. And so if you measure from that oxygen minimum zone, you can assume a certain validity for the entire oxygen minimum zone because that entire zone is remotely mixed. We have to be careful, though, if your question is particularly border interested. So, for example, what happens where the oxygen minimum zone starts to change? Then, of course, that data point, if it comes from the center of the oxygen minimum zone, is not necessarily valid anymore. But ultimately, we can take strategic measurements or strategic cores to get a measurement that is valid for a larger region than just the location we took it from. Additionally, I do have to say that this field is called paleoclimate. Paleoclimate has been going on for a while. And so by now, we actually have thousands of cores. So what we really do these days is take multiple cores and average, not just average blindly, but look at the different signals and see if they're the same or not. And then we average them if they are the same. So for example, one of my publications looked at the Indian Ocean and its ocean circulation. And what I found was that if I look at cores along a certain flow path, and I looked at something like 8 cores across the entire Indian Ocean from east to west, they all had the same signal over the last 1 million years. And that is obviously a really interesting point. So it led me to discover a new feature of the Indian Ocean, whereby ocean circulation in the Indian Ocean works in a potentially different way than the other two oceans. But that was visible to me because we had so much data already. So when we take a sediment core today, that sediment core is not sort of like alone any longer. We often have a suite of sediment cores nearby that have already been worked on and that can be used for comparison. I do want to add one more thing because we've talked about CO2 earlier and how we reconstructed CO2. Now, CO2 is an interesting one because usually what we reconstruct is ocean parameters. It is fairly rare that we go back to something that is an atmospheric signal. Usually we stay with oceanographic signals. So, for example, we reconstruct sea surface temperature or bottom water temperature or salinity or...
acidity as well, or not?
Yeah, acidity via pH. But this very specific, because the pH is so closely linked to the CO2 concentration in the ocean, which is so closely linked to the CO2 in the atmosphere, it is a very unique system that we can actually go back and calculate atmospheric signal in this case. And that is an interesting one because the atmosphere mixes so fast compared to the ocean on a matter of days, weeks, months, whereas in the ocean we have an overturning. Like if you throw in a grain at one end of the ocean, it takes 1,000 years for that grain to go back to where you threw it in. So the mixing is much, much longer. And that means that we can effectively say that whatever CO2 we back calculate is a global atmospheric signal because that atmosphere has mixed 1,000 times by the time that we have made our or that integrates our measurement, the time that is integrated with our measurement. Nonetheless, though, in our study, we did the extra mile and we didn't just took one sediment core, we took 3. And it's actually the first time in history that has ever been done for CO2 reconstructions.
Okay, you mentioned that my question was also related to some of the discussions you have among the scientists, right? The data points and how much do they cover. So I was wondering, I know that a couple of weeks ago you were at a conference as well, and I sometimes go to conferences myself too, and sometimes I am okay, and sometimes I get very frustrated because I cannot follow almost anything, right? So it's really like a very much deep in discussions. So if you were to take me to your conference, what are the discussions there? What are people doubting, quarreling about? I don't know. What is the point that is for of course, paleoclimate or whatever you were discussing at the conference?
So I think what is at the moment something that we're all very interested in is and I think that might be, the listeners might be interested in this, is the change in the Gulf Stream. For Europe, very important issue because the worry is that if the Gulf Stream slows down, maybe Europe experiences, and here in the media you can read whatever you want. You can say we might get an ice age, or you can read we don't get anything, or it will be so cold, or it will be so hot. Like you find all kinds of things. And actually in this case, that is that conference discussed that quite in big detail. I saw some very, very interesting new data on trying to reconstruct the Gulf Stream. And I had a really interesting discussion about that as well yesterday at lunch with one of with just random citizens that I was sitting at the same table with. And I wanted to share what the conference is saying. So please bear in mind that this is ongoing research, and this is just because of what I said earlier. Do not walk away and feel anxiety, because ongoing research means we're making progress. We're getting there. This answer is going to come in the next months or year or two. So keep yourself posted and see what comes out. But the interesting thing is, at the moment, we cannot quite grasp yet how this system is really going to respond. So what we know is how this system works. First, the Gulf Stream, we like to call it the Gulf Stream, but the Gulf Stream is part of the entire overturning circulation. So when we say that the Gulf Stream slows down, we have to remember that it's not just the Gulf Stream. It would mean that the entire global circulation would slow down. And the reason why this might happen is because in the north, we call this the Nordic Seas, or in the Arctic Seas, we currently have a lot of Greenland ice melting, and fresh water hinders the density development of the water. And so therefore the water doesn't sink as far. This is because the saltier your water, the further it sinks. But if you put in a lot of fresh water, you're obviously diluting that salt. And so you don't create as heavy waters any longer. And if you don't sink it as far, potentially that means that you're going to alter the way the waters circulate through our global oceans. But what we forget, and this is one of the major discussion points, is just because you don't sink it as far, it doesn't necessarily mean that it doesn't run as far. So you can sink it only half the way down, but maybe it actually speeds up because it now just needs to follow a shorter path. And all you're doing, well, not all you're doing, it's a big deal, but what you're doing is you're isolating the deep ocean, which is now not getting any mixing at all. But that doesn't necessarily then slow down the Gulf Stream. So it doesn't necessarily mean any climatic influence for Europe at all. Alternatively, we've seen some very new data that shows where scientists have calculated in a climate model what if it slows down, but what also if at the same time we know now what our global warming projections are. What if we put them both into a climate model? Because sometimes as scientists, we like to isolate the effects. We like to look at one only. But ultimately, looking at the Gulf Stream without a climate effect is not realistic for humans, right? Because that's not what's going to happen. So looking at both of them coupled, a couple of years ago, the results showed that they cancel each other out. So the cooling of a reduced Gulf Stream is actually the same as the warming of the global warming in Europe. Now, at that time, we thought, maybe Europe is actually a great place on the planet because nothing's going to happen at all. But now, the newest results actually show, again, something different. So they show that if you change the models or the effect of how climate change impacts, it couples itself to the whole system, you actually see that global warming outdoes the cooling of the Gulf Stream. So we would still experience warming. Now, again, that is a model, so we haven't shown this in real data. And now on this conference, we saw a lot of colleagues from me that do the same thing that I do, but they do it for the Gulf Stream. So they go back in time, they use natural archives, and they reconstruct the Gulf Stream. And what they're showing is that the Gulf Stream is incredibly variable, but has been shifting over the Holocene period. So the Holocene is the last 8,000 years or so. It has been slowly slowing down. They've definitely shown a slowdown in their data, but a slowdown again in those kind of reconstructions. It's hard to disentangle whether slowdown means true slowdown or whether slowdown means shallowing, meaning, the cell changes. So that is one of the scientific discussion points, because ultimately we can get at this by looking at multiple cores that are located in different depths of the ocean. And so we want to see, do we see the change in the signal in different depths? And my colleague presented his brand new work where he did this, and there was a huge discussion, over, well, can you interpret that data this way? Is there a way how you can interpret this data without concluding that? So you can see that as scientists, we spend an entire week basically sleepless discussing these kind of results and making sure that whatever actually is being communicated and in the end what we call published is an incredibly rigorous process, and whatever comes out is usually something that has gone through multiple conversations where many people have criticized, have put ideas forward, have considered, is there alternative possibilities? Can we explain this in another way? And sometimes you even pause your work and test something else just to make sure that what you conclude is real. So yeah, this was one of the hot topics 2 weeks ago in Glasgow.
It sounds very interesting, actually, I have to say. But I want to circle back just to finish off with the beginning of our conversation, where you said that, okay, you wanted to show more clearly, let's say, what is going on with climate change and provide more data and be better at convincing people that it's there and it's happening and that we should be doing something about it. But then again, when we continued discussing, you were rather telling me about the past data, right? And you could argue that, okay, it's great to see that the temperatures were not rising this much and CO2 levels were lower in the atmosphere and all that, but how does it help with now? Because I don't see the link.
Sure, absolutely. You're not the only one who doesn't see the link. The important thing is to understand what I would call the baseline. So we can only say whether our current climate is changing and by how much if we know what happened before humans were here. For example, kind of what I tried to say earlier, if our current data just shows an increase, it just shows that we go from A to B, from down to up, we don't know. That could be normal, because if we now zoom out, maybe that down to up is actually a section of a sine curve, and it'll go back down in just about 100 years, and then it'll go back up in 100 years, and it'll go back down in 100 years.
So we are not sure about this?
We are sure about this. But my point is, just by looking at modern data, we wouldn't know. We wouldn't know. We are required to go back in history to understand whether what we see today is out of normal or normal. Because if it is normal, that has different implications for how we as humans might want to deal with the climate change. We also want to know, for example, whether what we are doing is reversible or not reversible, right? So we might want to know whether it is human-made entirely, because if it is not human-made, that means that we can continue our status quo, which means that we have built a society at the moment based on fossil fuels that runs pretty comfortably, and taking these fossil fuels away is an effort on our behalf. So if it really shows that wouldn't be the case, if this was a fact that just happened naturally, and maybe it just happens every 300 years, so we just happen to go up now, and in the next 300 years we're going to go down. Humanity has lived for longer than that, right? Like the Romans were around like 2,000 years ago. So in that case, we could be relaxed. We could say, okay, we might be a bit hotter now. The Romans did it too. It was actually a bit cooler, just for interest, during the medieval times. Was a bit colder. People dealt with it. In fact, there is thoughts whether that has a link to the Great Plague outbreak. I mean, a huge deal with that is the sanitation conditions that we had at the time, but also if the climate is a little bit colder, maybe our immune systems are a little bit weaker. Hypothesis, I'm not saying whether it's true or not, but like we would approach these changes with an entirely different mindset. But now we know that this is not the case. We know that in the last 1.5 million years, the CO2 has never been this high. We know that the CO2 was maximum in 1960 already compared to the last 1.5 million years. So, and we know now that the change happened faster than anything we measured over the last 1.5 billion years. That tells us something, because it tells us that we are going into a world that we as humans don't know. I mean, humans evolved over the last 2 million years. So the first sort of hominids walked the earth around 2 million years ago, and the first big civilizations usually we consider happened within the last 8,000 years. So to give like a rough perspective, and we are way out of the last 8,000 years. We are way, way, way out of the last 1.5 million years. So we are already in a world, in a CO2 world that is different from what hominids have ever experienced. And that now puts up questions of evolution. Are we evolved to handle such a high CO2 and ultimately a high temperature because of the greenhouse effect? Can we do that, or are we evolved in a different way? Or Or what about the other life that is on the planet? Is that evolved for this kind of climate? And we are already noticing that we are already losing so many species that scientists are talking about a mass species loss, so mass extinction event, which the Earth, by the way, has had before as well, which we also just know because we do science in the past. So we know that the Earth has had 5 extinctions events already. They obviously happened naturally, but ours happens due to human greenhouse gas release. Yeah, that's an ethical question now. How do we feel about that? But it throws up all these questions of mitigation. How do we as humans deal with this new state of climate that obviously we have never been in touch with? How do we feel ethically about our planet and about other species that are now having to evolve in this kind of climate, because they don't have technology. We have technology. They don't. Is technology and evolution, are they going to be fast enough? Because we have an incredibly fast rate of change. 1960 to 2026, that's not even 100 years. And so we have a very, very fast range of change. And so is evolution going to be fast enough to upkeep that? And is our technology fast enough to upkeep that? These are all questions that we need to ask ourselves, and we're asking them already, and we are thinking about mitigation already, but that's all because we know. We couldn't have known if we hadn't gone back in the past.
You ask so many questions and we don't have time to now unwrap them all and consider the answers. And of course, I never like to finish the podcast without really saying what we can do. But I think we will have to do it this time, because that will, again, take another 40 minutes to discuss how to do it. I also promise you that in the show notes, we will share all the different places where you can get information, and also all the related episodes where we're discussing also what you can do, all the citizen science projects and all the other things where you can get involved. And we will share the links to all these art projects that you talked about that are very, very interesting. I actually discovered them as well recently, and it looks cool. I have never been to Taiwan, so I cannot check it out. But maybe one day, why not, listeners? You will have the link. Go and see all that is happening, because there's a mural appearing as well, right? In a school and all that. And what remains is, first of all, to solve the pub quiz question, which I cannot exactly, because as I said, we are recording before Young Women's Conference, which means that I don't have the data, but you will be able to. So remember, you can go to the website, ywc.lu. You can also check us on all the social media where we're present. We will be announcing all the numbers we had. And remember, we hope to continue with this. So if you want to get involved, to reach out to us as well. And what I can do is just to thank you, Sophie, very much for today.
Thank you so much. And everyone out there, thank you for listening. I hope you've learned something. This was exciting to you. Send me an email if you would like to. Thank you so much.
Exactly. We will also obviously share all the contact details in case you want to reach out to Sophie. This was SciLux, and my name is Hanna Siemaszko.